Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as oscillation. Let's see composition of two SHMs. Having same period and along same path. Right? Now let's consider that a particle can be subjected simultaneously to two or more SHM in different periods, paths and amplitude. But what we are going to consider is that we are going to take a very simple case of composition of two SHMs having the same period along the same path but different amplitudes and different initial phase. Right? So what we will do is when a particle is simultaneously subjected to two SHM, its resultant displacement at any instant will be equal to the vector sum of the displacement of the two SHMs at that instant. That's exactly what we are going to try to prove. Right? Let us consider two SHMs with same period, same path, but different amplitudes, and different initial phases. Right, in which case I can say that they can be represented by the equation. They can be represented by the equation x1 is equal to a1 sine omega t plus alpha 1 and x2 is equal to a2 sine omega t plus alpha 2. Right, where alpha 1 and where a1 and a2 are the amplitudes of the two SHM and alpha 1 and alpha 2 are the initial phases of two SHM. Where I can say that a1 and a2 are amplitudes and alpha 1 and alpha 2 are the phase. Fine, we get the same here. Now, once you have this, let the angular velocity omega is same for both the SHM. The angular velocity omega is same for both SHM. Right? And we also know that, therefore I can say that time period 2 pi by omega, t is 2 pi by omega, is also same on the same path. Right? Once we have this, now let us find out the resultant displacement of these two SHM. The resultant displacement x of the two SHM can be given as is x is equal to x1 plus x2. The resultant displacement is going to be the sum of the two displacements, in which case I can therefore say that x is equal to x1, that is a1 sine omega t plus alpha 1 plus a2 sine omega t plus alpha 2. Right? Now this can be written as x is equal to a. Here I can use addition formula, sin a plus b, sin a plus b is sin a cos b plus cos a sin b. So this can be written as sin omega t cos alpha 1 plus cos omega t sin alpha 1 plus A2, same formula again, addition formula, sin A cos B plus cos A sin B. Fine, do we get this thing here? Now this can be written as, open the brackets and simplify. X is equal to A1 sin omega t cos alpha 1 plus A1 cos omega t sin alpha 1 plus A2 sin omega t cos alpha 2 plus A2 cos omega t sin alpha 2. So you can here in the first and the third term you can take sin omega t common. If I take sin omega t common, I'll get A1 cos alpha 1 plus A2 cos alpha 2 sin omega t plus A1 sin alpha 1 plus A2 sin alpha 2 cos omega t. Right? Now let us assume that A1 cos alpha 1 plus A2 cos alpha 2 is nothing but R cos delta. Let us assume that A1 cos alpha 1 plus A2 cos alpha 2 is R cos delta. Similarly, A1 sin alpha 1 plus A2 sin alpha 2 is R sin delta, in which case I will get displacement x is equal to R cos delta sin omega t plus R sin delta cos omega t. Right? So in that case I can say this is sin A cos B plus cos A sin B, which can be written as sin A plus B R sin delta plus omega t, but A sin delta plus omega t represents an SHM, therefore the resultant displacement will also be SHM. This equation is in the form of an equation of an SHM. X is equal to A sin omega t plus alpha. See, I can rearrange this and write it this way. R sin omega t plus delta, where R is the amplitude and delta will be the initial phase of the resultant SHM. Fine, do we get this in here? So the above equation shows the resultant motion of 2 SHM, which will also be an SHM. The above equation shows the resultant motion of 2 SHM, which is also an SHM, of time period t. Fine, do we get this in here? Okay, now let us try to find out what will be the amplitude and the phase of this SHM. Right? Now we know that R cos delta is A1 cos alpha 1 plus A2 cos alpha 2. Also, we know that R sin delta is A1 sin alpha 1 plus A2 sin alpha 2. Right? Square both the sides and add them. Squaring and add. So in that case, you will get R square cos square delta plus R square sin square delta is equal to A1 cos A square cos square alpha 1 plus twice A1 A2 cos alpha 1 cos alpha 2 plus A2 square cos square alpha 2 plus A1 square sin square alpha 1 plus twice A1 A2 is cos alpha 1 cos alpha 2. Yeah, this is going to be a1 a2 sin alpha 1 sin alpha 2 plus a2 square sin square alpha 2. Right? Now this can be simplified further. On the left hand side, if I take r square common, I'll get cos square delta plus sin square delta, but cos square theta plus sin square theta is 1. So this can be written as r square cos square delta plus sin square delta. I am substituting as 1. Here I can write this as a1 square plus a1 square cos square alpha 1 plus, yes, you have twice a1 a2, then you have a2 square cos square alpha 1. I can take
a1 square cos square plus sin square.
a1 square sin square alpha. Yes, I have a1 square cos square alpha 1 plus a1 square sin square alpha 1 plus a2 square cos square alpha 2 plus a2 square sin square alpha 2 plus twice a1 a2 cos alpha 1 cos alpha 2 plus twice a1 a2 sin alpha 1 sin alpha 2. Therefore I can say that r square is equal to a1 square common cos square alpha 1 plus sin square alpha 1 is equal to 1. Cos square theta plus sin square theta is 1, so this will be a1. Similarly, a2 square common cos square alpha 2 plus sin square alpha 2 will be 1, so this will be a2 square. Twice a1 a2 common, in which case you will have cos alpha 1 cos alpha 2 plus sin alpha 1 sin alpha 2. Right, this can be written as r square is a1 square plus a2 square plus twice a1 a2 cos a cos b plus sin a sin b is nothing but cos a minus b. Take square root on both the sides, therefore you will get r is square root of a1 square plus a2 square plus twice a1 a2 cos alpha 1 minus alpha 2. That will be the resultant amplitude of the 2 SHM. Right? Now I want to know the phase of the 2 SHM. Right? We know that I can say again r cos delta is a1 cos alpha 1 plus a2 cos alpha 2, and r sin delta is a1 sin alpha 1 plus a2 sin alpha 2. Divide the two equations. In that case, I'll get sin delta upon cos delta. R and R will get cancelled. Or if you want, I'll show it to you. R sin delta upon R cos delta is going to be a1 sin alpha 1 plus a2 sin alpha 2 upon a1 cos alpha 1 plus a2 cos alpha 2. R and R gets cancelled, so you get tan delta is a1 sin alpha 1 plus a2 sin alpha 2 upon a1 cos alpha 1 plus a2 cos alpha 2. Therefore, you can say that delta is equal to tan inverse of a1 sin alpha 1 plus a2 sin alpha 2 upon a1 cos alpha 1 plus a2 cos alpha 2. That is going to be my phase of the 2 SHM, the resultant phase of the 2 SHM. Now, from this, what we understand is that the amplitude of the resultant amplitude of the 2 SHM depends upon the individual amplitudes of the 2 SHM, and it depends upon the difference between the phase of the 2 SHM. Right? I can say therefore the resultant amplitude depends on A, the individual amplitudes of the two SHMs and the difference between the phase of the two SHM. Right? Now once you have this, let's find out different possibilities in this. Let's consider case 1 if the phase difference is 0. Case 1, if phase difference is 0. Phase difference is 0, that means if alpha 1, therefore I can say that alpha 1 minus alpha 2 is 0. If alpha 1 minus alpha 2 is 0, then R will be square root of, or I can say R square will be nothing but A1 square plus A2 square plus 2A1 A2 into 0. Therefore I can say R square will be A1 square plus A2 square. Therefore R will be square root of A1 square plus A2 square. So if the initial phase is 0, then the resultant amplitude is going to be nothing but, wait, this is going to be cos of 0. Cos of 0 is 1. So this is going to be twice A1 A2. So therefore I can say R square is going to be nothing but A1 plus A2 the whole square. Therefore I can say R is equal to A1 plus A2. Right? So if the phase difference between them is constant, then the resultant amplitude is the difference between is the sum of the two amplitudes. Right? Next, case 2. If the phase difference is pi, if the phase difference is pi, that means I can therefore say that alpha 1 minus alpha 2 is pi. Therefore I can say that R square is equal to A1 square plus A2 square plus twice A1 A2 cos of pi. Cos 180 is minus 1. Therefore I can say R square is equal to A1 square plus A2 square minus 2A1 A2. Therefore I can say R square is equal to A1 minus A2 the whole square. Therefore R is equal to A1 minus A2. So if the phase difference between them is pi, then the resultant amplitude is the difference between the two amplitudes. Right? Next, case 3. If phase difference is equal to pi by 2. Right? In that means I can therefore say that alpha 1 minus alpha 2 is pi by 2. If alpha 1 minus alpha 2 is pi by 2, then I can say R square is equal to A1 square plus A2 square plus twice A1 A2 cos 90 is 0. So I'll get R square is equal to A1 square plus A2 square. Therefore R is square root of A1 square plus A2 square. So if the phase difference between them is 90 degree, then the resultant amplitude is the square root of the sum of the squares of the amplitude. Now, let us consider case 4 if the two amplitudes are equal and the phase difference is 0. Case 4, two amplitudes are equal. Right? Under that, let's consider the first alternative where we consider that the phase difference is 0. Two amplitudes are equal and phase difference is 0. That means I can therefore say A1 is equal to A2 is equal to A assume, and alpha 1 minus alpha 2 is 0. R square is equal to A1 square plus A2 square plus twice A1 A2 cos alpha 1 minus alpha 2. Right? In which case I can therefore say that R square is equal to A square plus twice A into A cos of 0 is 1. So r square is 2a square plus 2a square. R square is 4a square, therefore r will be equal to 2a. That means if the amplitudes are equal and the phase difference is 0, then the resultant amplitude will be the sum of the amplitudes. A, 2a. It will be twice the amplitude of each one of them. A is 5. If the two amplitudes are equal, and phase difference is equal to, say phase difference is pi. Phase difference is pi. Right? In which case then I can say that therefore A1 is equal to A2 is equal to A assumed, and alpha 1 minus alpha 2 is equal to pi. Right? R square is equal to A1 square plus A2 square plus twice A1 A2 cos alpha 1 minus alpha 2. So I can say R square is equal to A square plus twice A into cos minus pi, cos of pi. Cos of pi is nothing but minus 1. So in that case I'll get R square is equal to 2A square minus 2a square. So r square is 0, r is 0. So if the two amplitudes are equal and the phase difference is pi, then there will be no resultant amplitude obtained. Right? Case 6. If the two amplitudes are equal and phase difference is say pi by 2. That means I can therefore say that A1 is equal to A2 is equal to A assume, and alpha 1 minus alpha 2 is pi by 2. Right? I can say that R square is equal to A1 square plus A2 square plus twice A1 A2 cos alpha 1 minus alpha 2. So I can therefore say R square is equal to A square plus twice A into cos of pi by 2 cos 90 is 0. So R square is 2A square plus 0. Therefore R is A root 2. Then the resultant amplitude will be nothing but A root 2. Fine, do we get this thing clear? Next, let's see a simple pendulum that finishes your composition of two SHMs. Right? Second, let's consider a simple pendulum. Now, how do I define a simple pendulum? How do I define a simple pendulum? An ideal simple pendulum is defined as a heavy particle suspended by a weightless, inextensible string from a rigid support. An ideal simple pendulum is defined as a heavy particle suspended by a weightless and inextensible string from a rigid support. Right? That is a simple pendulum. Right? Now let's see this. So this is your rigid support, inextensible string, heavy particle. Right? Now let's see the three positions where it can go: here and here. Let's assume this is how your pendulum is going to oscillate. This is my field of oscillation. Let's assume that it covers an angle of theta over here, right? T is the tension that will be acting on the string, right? To counter that tension, the downward force will be the weight of the particle mg, right? Since mg is a vector quantity, it can be resolved into two components, one along horizontal and one along vertical, right? The horizontal component will be mg sine theta and the vertical component will be mg cos theta. The pendulum oscillates by an angle of theta. T is the tension on the string, right? The opposite force, to counterbalance this force, mg is the weight that is acting in downward direction. Since mg is a vector quantity, it can be resolved into two components, mg sine theta and mg cos theta. mg sine theta provides the necessary restoring force, whereas mg cos theta counterbalances the tension on the string. Fine, do we get this in here? So, and let us assume that L is the length of the string. Fine. Let's write this one down first. Let us assume let L be the length of the string. Let's assume L is the length of the string, M is the mass of the ball. Let's assume that L is the length of the string, M is the mass of the ball, and it is displaced by a small angle theta when released. And it is displaced by a small angle theta when it is released. Right? In which case I can say that in the displaced position, the forces that act on the bomb are, in the displaced position, the forces that act on the bomb are right, let's see all the forces that are going to be acting on the warp. 1. The weight mg of the warp that acts vertically downward. Weight mg acts vertically downwards. That is the weight of the warp. Next, tension T in the string. Right? Now I can say that the force mg due to the weight of the warp can be resolved into two components. The force mg due to the weight of the warp can be resolved into two components. 1. Mg cos theta acting along the string. Mg cos theta acting along the string. And second, Mg sin theta perpendicular to the string. Right? Now, as there is no motion of the string, that means mg, there is no motion of the string in vertical direction. Therefore, I can say that mg cos theta counterbalances the tension on the string, right? As there is no motion, therefore mg cos theta balances the tension on the string, right? Therefore, I can say that mg cos theta should be equal to T. Now, the component mg sin theta acts towards the mean position. Sorry, the component mg sin theta acts towards the mean position and hence tends to restore the bob to mean position. Therefore, I can say that mg sin theta serves as the restoring force. I can say that mg sin theta acts towards the mean position the force mg sin theta acts towards the mean position. It tends to restore the bob to mean position. It tends to restore the bob to mean position. It tends to bring the bob back to the mean position. Thus, mg sin theta acts as a restoring force. Therefore, mg sin theta acts as the restoring force. That means I can say that mg sin theta will be equal to restoring force F. Right? Once I have this, then I can say that F is equal to minus mg sin theta. Right? The negative sign in the expression indicates that as theta increases, the direction of the theta increases as the direction is opposite to the force. The force is acting in this direction and theta is going to increase in the other direction. Right? The negative sign indicates that theta and F are in opposite directions. Right? So I therefore get F is equal to minus mg sin theta. Now, I can say that acceleration A is equal to F upon m. You can say acceleration is nothing but F upon m. So therefore this is going to be F is minus mg sin theta upon m. So that's minus g sin theta. So the acceleration that is going to be acting on the bob is going to be minus g sin theta. But theta is very small. Since theta is very small, for very small angles, sin theta is approximately equal to theta, right? Therefore, I will get acceleration is minus g theta. Instead of sin theta, I am writing that as theta. Now, I can also say, so guys, look at this. The length of the arc should be equal to the radius. S is equal to r theta. So the length of the arc should be equal to radius into angle. That means I can therefore say that by definition, the length of the arc, let's call this point, guys, as A. Let's call this point as, say, B. So I can say that arc AB is equal to radius is L, S is equal to r theta. So arc AB is going to be equal to L into theta. Therefore, I can say that theta is arc AB upon L. Right? Now, let's assume that this displacement, since theta is very small, I can consider AB to be the straight line. Since theta is very small, therefore AB is a straight line. Right? Let's assume that the mean displacement from the mean position is x. Right? Let us assume that it represents, and it represents displacement. It represents displacement x from mean position. In that case, I can say theta is x upon L, right? In which case I will get acceleration. Acceleration is minus g theta, so that will be minus gx upon L, right? Where I can say g and L are constant. G is the gravitational force, L is the length of the pendulum. That means I can therefore say that acceleration here is directly proportional to the displacement from the mean position, and acceleration is directed towards the mean position. That means the displacement and the negative sign here indicates that displacement and acceleration are in opposite direction, right? I can say here G and L are constants, right? Since G and L are constant, therefore I can say acceleration is 1, directly proportional to the displacement from mean position is directly proportional to the displacement of the bob from the mean position, and second, it is also directed towards the mean position. It is also directed towards the mean position. Right? Hence, I can say that the motion of the bob is a linear SHM, because these are the two conditions that you require for linear SHM. Right? I can say therefore the motion of the bob satisfies the two conditions required for a linear SHM. Right? Hence, the motion of the bob is a linear SHM. Hence, motion of bob is linear SHM. Right? That's how you prove that a pendulum is a linear SHM. Right? Now, in that case, I can say that in magnitude, acceleration is going to be nothing but gx upon L. That negative sign was indicating that acceleration and displacement are in opposite direction. If this is the acceleration per unit displacement, acceleration per unit displacement is going to be nothing but g upon L, because for unit displacement, that is, I'll divide by the displacement x. Now we know that time period of an SHM is nothing but 2 pi upon acceleration per unit displacement. We have derived this. I can say that, but time period of an SHM, t is nothing but 2 pi upon square root of acceleration per unit displacement therefore I can say that time period is 2 pi upon root of g by L, right? Therefore I will get that time period t is nothing but 2 pi root of L by G. That is the time period of a simple pendulum. Fine, do we get this thing here? So the time period for a simple pendulum is 2 pi root of L by G. Right? Now, From this, we understand the laws of simple pendulum. This expression gives you the laws of simple pendulum. Second is simple pendulum. Third, laws of simple pendulum. Laws of simple pendulum. First, the period of the simple pendulum is directly proportional to the square root of length. Period is directly proportional to square root of length. Second, the period of the simple pendulum is inversely proportional to the square root of acceleration due to gravity. Period is inversely proportional to the square root of acceleration due to gravity. Right? And third, the period of the simple pendulum does not depend upon the mass. Period of simple pendulum does not depend on mass. Right? Those are called as laws of simple pendulum. Next, what do we understand by a seconds pendulum? What do we understand by a seconds pendulum? A seconds pendulum is defined as a pendulum whose time period is 2 seconds. Right? Definition. A simple pendulum whose period is 2 seconds is called seconds pendulum. Right, that is what is a seconds pendulum. Right, that means we know that for a simple pendulum, T is equal to 2 pi root of L by G. Right, we've said that for a seconds pendulum, but for seconds pendulum, T is equal to 2, therefore T is 2 is equal to 2 pi root of L by G. 2 and 2 gets cancelled. That means in that case I will get 1 is equal to pi root of L by G. Squaring both the sides, if I square both the sides, I will get G upon pi square is equal to L. But we know the value of G and we know the value of pi. We know the value of G for a particular place. It could vary from place to place. So whatever the place, you will know the precise value of G. The value of pi is also known to you. So by varying the length for a given place, you can make a seconds pendulum for that given place. Fine, do we get this thing clear? Thus, for a seconds pendulum, the length of the string in the case of seconds pendulum depends upon the acceleration due to gravity at that place. Right? Okay, we'll stop this here for the day. Thank you very much.